Alright, we're going to conclude section 15.7 in this video, and we're going to work an exercise on page 1054. We're going to do number 12, which says, so we don't have any directions, explicit directions. Alright, so number 12 just says let f of x, y, z be equal to the vector field f is 0, 0, yz. And let C be the boundary of the part of the cone z equals the square root of x squared plus y squared in the first octant between the plane z equals 2 and z equals 3. Give the counterclockwise orientation to the part of C in the plane z equals 2 and the clockwise orientation to the part of C in the plane z equals 3 as seen from above. Use Stokes' theorem to evaluate the line integral over C of f dot dr. Alright, so we need to evaluate that line integral by instead doing the double integral. But first, let's kind of orient ourselves with this surface and figure out what we have going on here. So I'm going to actually sketch the surface this time. Sketch it over here. Alright, so the surface is a portion of a cone, but just in the first octant, and it's also, there's still that part of that even is cut off as well. So let's see. Actually, when you sketch this, just sketch like a dotted line right here, because the cone is actually, when none of this part on the inside would be included in the cone, so we don't want to have any part of our surface indicated right there. So we're just in the first octant, and this is z equals 3 right here that we're sketching, and then we'll go down to z equals 2, and we'll put that so we can see clearly. Put z equals 2 right here and do the same thing. It's dotted lines and then a smaller curve than that one that we had above, like that, and then we'll connect that to that and connect that to that. Alright, so that's the portion of the cone that we have. And they said when we view this from above, give the counterclockwise orientation to the part of C in the plane z equals 2. So if we were looking down on this curve down here at the bottom, it said we should have counterclockwise orientation. So the arrow will be going that way down there. And clockwise orientation to the part of C in the plane z equals 3. So if we were looking down on this thing, this part would have clockwise orientation. So that's the orientation. Now our surface actually is the cone itself, that portion of the cone, of course. So now, given that these orientations we have here, and that being our surface, they only gave us those two parts. But now, of course, that dictates how we would have to go around the boundary curve. And remember, the boundary curve on this thing is just where you see the solid lines on here. Nothing else is included in the boundary curve. So now that it dictates that this arrow would have to go that way, and this arrow would have to go that way. So now from that information, what we need, if we were evaluating the line integral, that would be sufficient. But we're not evaluating the line integral. They told us to use Stokes' theorem, saying we have to do the surface integral. So we need a normal vector now based upon this. So now we imagine our stick figure. We don't right now know if our stick figure's head will be pointing out towards us or if it will be pointing kind of towards the z-axis instead. That's what we have to figure out. Now, with the stick figure's head pointing, and you just imagine each scenario and figure out which one works. If the stick figure's head were pointing out at us, and the stick figure were to walk in the direction of these arrows, because the arrows have forced the stick figure's hand now to walk in that direction. He or she has no option. So now, should the head be pointing out at us or pointing in, to ensure that this shaded region stays to the stick figure's left at all times. The stick figure's head would actually be pointing out towards us in that scenario. So this would, because of the tilt of the cone, if they were to actually word this in the problem, they would say downward orientation on that normal vector, because it's always kind of pointing in a downward direction. So this would be our normal vector in, because we're going to need to know is our normal vector point up or down when we set everything up. And then we'll decide that we need a plus or minus sign in front of our integral based upon our parameterization that we use. All right, so now this is, I probably should have written this a long time ago, but this is z equals the square root of x squared plus y squared is our surface. And we were told that z is between 2 and 3. So that tells us that the square root of x squared plus y squared is between 2 and 3. And this is just what we have sketched over here. So this is our surface S, and these are the bounds for the surface. And now we get to choose how we want to parameterize this surface. So since they've already solved for z for us, the natural thing is to use our favorite parameterization, which is x equals x, y equals y, z equals f of xy, which is x squared plus y squared, and then our bounds, the square root of x squared plus y squared between 2 and 3. All right, and one thing to keep in mind is that I'll write bounds this way for a problem where we're actually going to evaluate an integral. But in a problem, if you were just flat out asked to parameterize a surface, you should not write your bounds this way. You should you should be able to get x is between something, something, where there's constant, function of function, and y is between something and something. So if you were just asked to parameterize this surface, this would not be sufficient. You would need to go a step further, and the way you would end up doing that for this is by deciding to parameterize in, say, cylindrical coordinates. But for our purposes, this is perfectly fine because we're going to have to address this anyway when it's time for us to evaluate our integral. All right, so now, or let's actually take that. Let me do this though. The way we had it is fine, but I'm going to write it this way just because that's what we're a little more accustomed to working with, is that. All right, so now we're ready to set things up. So I need to make sure I can still see f because we still need to find the curl of f. But, or actually, let's do that now, and then we'll set up our integral so we don't forget. So the curl of f here is going to be, and for sake of time, I'm going to do this in my head instead of writing it out. Partial of that with respect to y, z, and then minus that. So we're going to get z. And luckily this is going to be easy as well because the zeros, 0 and 0, z 0, 0. All right, there we go. So there's our curl. So this is m, that's n, and that's p. All right, so now we were told to evaluate the line integral over c of f dot dr, but we were told to use Stokes' theorem, which means we have no choice but to instead evaluate the surface integral over s of curl of f dot n ds, which for us, because we used our favorite parameterization, that's already set up for us, and that is equal to the double integral over r of negative m times f sub x minus n times f sub y plus p dA. Now remember, this formula has it written in that the normal vector in this formula points upward, but our normal vector points downward. So that means we need to put a negative sign in front of this. So that's actually what we should have there. So now we're ready to go and substitute everything in there. So we'll take our parameterization, substitute it in for m, n, and p into all of those, because m is a function of x, y, and z, n is a function of x, y, and z, and p is a function of x, y, and z. And then we take our partial of f, which this is f right here, with respect to x and y. And we'll put all of that information in there. So we get this is equal to, and we'll still just write r, the negative sign that we had there, the double integral over r of our m is just z, but we have to substitute our parameterization into there. So our m really ends up being the square root of x squared plus y squared. So we get the square root of x squared plus y squared, so negative square root of x squared plus y squared, so negative square root of x squared plus y squared times the partial of f with respect to x, and the partial of this with respect to x is just going to be x over the square root of x squared plus y squared. So x over the square root of x squared plus y squared, then minus n, oh, there's just 0 times f sub y, but I'll write it out, 0 times f sub y is not going to matter now, but we'll do it y over the square root of x squared plus y squared, and then plus p, so plus p is 0 dA. And so these last two terms go away, and on these first two terms, the first term, excuse me, that cancels, which makes our life easier. So we just end up with negative x. So we just end up with x. So this equals the double integral over r of x dA. Now we look at, we look at our region R, which is this region right here, and let's sketch that. So, so am I missing something? I think I am. X squared plus y squared. That, oh no, okay, I already have everything. So, sketching our region. So we have that, we have a circle of radius 2, but just in the first octant, first quadrant, now that we're drawing this, because our surface was in the first octant, and then a circle of radius 3. So this is 2, that's 3. So we take those quarter circles, and we see that region right there is a polar region. So the natural thing would be to change this double integral and do it in polar instead of rectangular as we have it. So this now, here our theta goes from 0 to pi over 2, and our radius goes from 2 to 3. 0 to pi over 2, and 2 to 3. Our integral is just x, so that's r cosine theta, and then we switch to polar. We switch a rectangular integral to polar. We didn't use a polar parameterization, so we need our Jacobian r and dr, d theta, and we would evaluate that integral. All right, so that concludes section 15.7, and we'll start section 15.8 in our next video.